Welcome to the second part of acids and bases. We're going to look at what does the pH scale actually measure. We've seen like the pH scale, and there's stronger acids and weaker acids and stronger bases and weaker bases, but what in the world makes them different? And how are acids actually different from bases? So that's what we're going to try to look at. So what is the actual pH scale measuring? So first, let's look at what's different about acids and bases. So first, this is a question that gets people messed up all the time. Which is more dangerous? Is it that acids are more dangerous? And it's true. I mean, most people think, oh my goodness, it's an acid, it's dangerous. And that can be true. In fact, I am straight up scared of our concentrated hydrochloric acid in the cabinet. They can be dangerous and totally caustic and burn your skin off. That is absolutely true. And I'll show you a video about that.
Okay, you can remember using hydrochloric acid for things, and oftentimes I'd have them in these bottles that said 1 mole per liter or 3 mHCl. And now, in the past, I've said, oh, this is 3 molar HCl. It's stronger than 1 molar HCl or hydrochloric acid. And we're going to figure out why that is. This is the difference in concentration. And I just wanted to show you how I make this hydrochloric acid. And I'm not going to do it here because I'm all alone in this building. And if anything happens, nobody will be here to hear me scream. So I'm just going to show you. This is where we keep the crazy strong hydrochloric acid, and we've got a bunch of different hydrochloric acids all mixed up. Oh, it's stinky in here. It smells like hydrochloric acid. But do you notice that thing? That is the hydrochloric acid that is concentrated. Is 37% hydrochloric acid, or 12 molar. Can you guys see that? 37% hydrochloric acid. We'll do some calculations with that, and I ain't going to touch that at all. We're just going to close the door right now.
But are all acids dangerous? I'm pretty sure you can think of some examples of acids that we looked at last time that are not dangerous. Pop, pretty sure you're not scared of that one. Lime juice, oh, scary lime juice. And that's a 2 on the pH scale. It's way down here on the pH scale. And vinegar is also an acid, but we wouldn't consider them dangerous. Okay, so then bases. Bases aren't dangerous, except they totally are. They are very dangerous and totally corrosive, and they will burn your skin off. In fact, bases can dissolve away your entire body. It's a new way to cremate bodies called water cremation. And there's a link here on the if you go into the slides presentation. And I was going to show this, but I don't want to. If you're a little squeamish, you might not want to watch it. But if you've already seen Fight Club and you don't mind a bit of gross, the chemistry is very good and accurate in the soap making scenes of Fight Club. So I have a link here if you want to go and click on that and look at it. And it will also show you that bases are dangerous and will burn your skin off. And it's a good example of lye, sodium hydroxide, that they use to make soap. And sodium hydroxide, I've had to work with it a lot, and trying to mix that stuff up is very scary. You have to put on the whole face shield and the apron, whole deal. Same thing with acids. Whenever you're working with concentrated acids, you're putting a face shield, a rubber apron, the big gloves, whole deal. You have to do the exact same safety stuff with both concentrated acids and concentrated bases. So those are dangerous, but are all bases dangerous? I'm pretty sure you can think of some examples that are not dangerous. Like soap. Woo, soap. Okay. So how do we know which acid or base is more dangerous than the others? And the answer is the pH scale. Luckily, the pH scale can tell us whether something is more acidic this way or more basic, working your way down to the purple. So more toward the pink with the universal indicator tells you that it is stronger acid, and more toward the purple means that it is stronger base. The problem is that the indicators stop changing a whole lot once they get to 1, and once they get to 12, they're pretty much the same color as well. So the strong bases and the strong acids kind of, like it's hard to tell the extremely strong bases and acids. So anyway, so I'll get into, I might have to cut this part out for a second. So let's look at what makes something acidic or basic. So if we look at the chemical formulas of some common acids and bases, especially the strong acids and bases, we get an idea of what makes a base. And I'd like you to look at this list. We've got hydrochloric acid, HCl, sulfuric acid, H2SO4, hydrofluoric acid, HF, nitric acid, HNO3, acetic acid, HC2H3O2, that's vinegar, carbonic acid, that's what carbonated water has in it, that's what makes it acidic, that's H2CO3. Do you notice any similarities between all of those formulas? Okay, I'll let you think about that for a little bit. But let's look at bases over here. Sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide. Okay, and ammonia. Well, anyway, but yeah, I'm hoping you noticed a pattern here with the hydroxide on all of them. So yes, there has to be something to this, that it has to do with this hydrogen, this extra, you could think of it as an extra hydrogen on all of these acids that make them acids. And then for the bases, do you notice this OH, the hydroxide? That's what the OH is. It's called hydroxide, are on all of these. And of course, ammonia is a base, but nothing's, there's always exceptions in chemistry. I figured I'd show you. There's exceptions on the acid side too, but let's not think about those. Let's think about the simple stuff. Okay, so what makes something acidic or basic? Acids have hydro, or H, at the beginning, and bases have hydroxide at the end. It's a really good clue that it's an acid or a base. And the reason that is because when you have these two together, remember, if you think about them as ionic compounds, we have a positive side, a cation, and an anion. So here's our cation, is the H+, so the positively charged ion of H, and then the negatively charged anion of chlorine, and those two get attracted together and make HCl, hydrochloric acid. So this H+ is what's in the water and it reacts with water and makes things acidic. Oops. And then the bases, you notice that this is also an ionic compound. It's an actual ionic compound because it has a metal. So we've got this sodium, which is positively charged, that's the cation, and then we have this OH is the negative anion, that's the hydroxide, and that hydroxide goes into water, and that is what makes things basic, is more of these in the water, and more of these in the water make it acidic.